And now for the exciting conclusion with logarithms. What we're going to do for the last few bits of this lesson is we're going to evaluate expressions involving logarithms, and the main way that we evaluate expressions with logarithms is by understanding what a logarithm is, and that's why I keep stressing that relationship between exponential functions and the logarithm being inverses. So as the inverse of an exponential function, the logarithm basically undoes the work of the exponential. And so basically, what I want you to do is anytime you read a logarithm, I want you to read that logarithm as, so I know technically it's log base a of x, but I want you to ask yourself a question in your mind. And that question is, a raised to what power equals x? And by kind of asking yourself that question, you can often solve lots of logarithmic expressions. The other thing you could do is switch from logarithmic form to exponential form, and that's another way to evaluate a logarithmic expression, kind of change from one language to another, maybe an unfamiliar language to one that's more familiar. But part A you can do in your head, definitely. X equals log base 2 of 8, so you would ask yourself, 2 to what power equals 8? 2 to what power equals 8? And of course, you guys know that the answer to that question is 3. So we have x equals 3 as our solution. You could try part B, and that's x equals log base 2 of 16. The question that you ask yourself in your mind is 2 to what power equals 16? And of course, that's 4. So x equals 4. Now for part C, I've got x equals log base 10 of 1,000. You could ask yourself 10 to what power equals 1,000. Let's pretend that you kind of had a little bit of a brain freeze and you couldn't figure it out. That maybe you weren't able to answer that question. I know you guys can answer that, but let's pretend that you don't know the answer to the question 10 to what power equals 1,000. One thing you could do is take your logarithmic expression, translate it into an exponential expression, into something that's more familiar. It's log base 10 of 1,000 equals x. So remember that logarithms output exponents, and so I have to have 10 to an exponent equals 1,000. 10 to what power equals 1,000. And then you could figure out that x has to equal 3. For part D, you could go ahead and you could do that same thing again. 5 to what power equals 5 to the 11th? 5 to what power equals 5 to the 11th? Well, we know that that answer has to be 11. 5 to the 11th makes 5 to the 11th. Another thing you could notice, though, is notice this is a log base 5 and then 5 to a power. Log base 5 and the exponential function 5 to the x, those are inverse functions of each other. And so if they're inverse functions of each other, they're going to return whatever your input is, that's going to be returned as your output. So if you notice that inverse relationship, that can often make a difficult problem a little bit easier to handle. For example, part E does exactly that. Look at part E. I have 7 raised to the log base 7 of 941. Well, if you remember that 7 to the x and log base 7 of x are inverse functions of each other, if you remember that these are inverse functions of each other, then you would remember that whatever your input is into that composition, that's also going to be your output. So you know your answer has to be 941. That's the easiest way of doing this problem. Now there is a way of kind of phrasing this as a question, and that'll get you your answer as well. I think this is the easier way, is to remember that 7 to the x and log base 7 of x are inverses of each other. So we end up getting our answer. Part F, same trick again as part D. If we have log base r and r to some power, those are inverse, that represents inverse functions. The log base r is going to undo the work that r to the x does. So our input is 4, so our output is also going to be 4. You could ask yourself the logarithm question, though, r to what power equals r to the fourth, and of course r to the fourth equals r to the fourth. So it works either way. And then for part G, I've got x equals log base 2 of 1 over 32. You could ask yourself the logarithm question, 2 to what power equals 1 over 32. Let's say you're having a hard time solving that, then your other course of action would be to rewrite this expression in exponential form. So 2 to what power equals 1 over 32. And at that point, it's a little bit easier to see that the answer is -5. The reason being that 1 over 32 is 2 to the -5th power. And then finally for h, I've got x equals log base 7 of 1. Now technically this is a logarithm property. Log base a of 1 for any base. It doesn't matter if it's 7 or 15 or whatever, as long as it's a positive number base. The log of 1 is 0. Of course, you don't need to have that memorized, because if you understand logarithms, that should become obvious to us. Because if you ask yourself the logarithm question, 7 to what power equals 1? Well, 7 to the 0 equals 1. So x equals 0. There it is. The logarithm outputs an exponent. It's the exponent that would go on 7 to make 1. Okay, well, what we just saw in the problem we just did with log base 7 of 1 was we saw a correspondence between exponent properties and logarithm properties. We're going to take that to the next level, actually. And if you recall, the product property for exponents, a to the x times a to the y equals a to the x plus y. That property of exponents carries over to logarithms, which makes sense because logarithms are just another way of expressing exponents. So that property translates over to logarithms as log base a of xy equals log base a of x plus log base a of y. What's happening here is you're taking multiplication inside of the logarithm and you're turning it into addition outside of the logarithm. Likewise, the power property, if you think about how this is working for exponents, it's going to carry over to logarithms as well. If you have a to the n all raised to the x, the logarithm version of that property is log base a of x to the n equals n times log base a of x. The kind of easy way to remember this is if you have a single exponent inside of a logarithm, you could take that exponent out to the front and make it into a coefficient. Now, that only works if the entire quantity inside of the logarithm is raised to the n power. It has to be like a single exponent affecting the whole input into the function. But we'll kind of expand on that idea in a minute. And then finally, the quotient property. Well, if you remember the quotient property from exponents, a to the x over a to the y is a to the x minus y. There's an analog for that with logarithms. Log base a of x over y equals log base a of x minus log base a of y. So once again, what you guys should be noticing is that division inside of the logarithm turns into subtraction outside of the logarithm. So what we're doing is we're taking operations inside of the log, and they turn into different operations outside of the log. For the product property, you see that multiplication inside turns into addition outside. For the power property, you could see exponentiation inside turns into multiplication outside. For the quotient property, you can see that division inside turns into subtraction outside. We can use these properties of logarithms to do some pretty complicated things. Now, I would say that the main thing you should take away from this lesson really is understanding the big picture idea of what a logarithm is. That is, that a logarithm is the inverse of an exponential function, and that log base a of x is to be understood as x to a to what power equals x. So that's the main thing, the question of logarithms and the relationship between logarithms and exponential functions. That's the main thing to understand from today. However, these properties of logarithms, they're going to be really useful down the line. So we're going to practice with them a little bit. Please don't let this scare you, though. All we're really doing is taking these properties and just kind of applying them just for the sake of practice. So I have log base b of g times h to the fifth equals something. Well, remember that we have a power property which says that multiplication inside of a logarithm turns into addition outside of the logarithm. So this is going to be log base b of g plus log base b of h to the fifth. So multiplication inside of the log became addition outside of the log. Likewise, I have another property, the power property. If I have a single exponent inside of the log, I can turn that into a coefficient outside of the log. So I have log base b of g plus 5 times log base b of h. There it is. I could do the same thing on number 2. It's just a little more complicated. Now division inside of the logarithm is going to turn into subtraction outside of the logarithm. So I'm going to have log base b of 3m to the 1/2 minus log base b of s. Notice I changed that square root into a 1/2 power. That should work well for us because now I could take that power out. So I've got 1/2 log base b of 3m minus log base b of s. Basically what I did, guys, is a power inside of the log by the power property becomes a coefficient outside of the log. And then finally, take a look right here. I've got log base b of 3 times m. So I'm going to have 1/2 parentheses log base b of 3 plus log base b of m minus log base b of s. So what we did was multiplication inside of the logarithm turned into addition outside of the log. And then my final answer, once I distribute this 1/2, is 1/2 log base b of 3 plus 1/2 log base b of m minus log base b of s. Now this is now we could take problem number 7 and kind of turn it around. We instead of taking a single condensed logarithm expression and expanding it out like we did in the 2 previous problems, we're going to take an expanded expression and condense it down to a single logarithm. So I can use properties of logarithms to go in either direction. I can either expand or I can contract. For number 1, addition outside of the logarithms is going to turn into multiplication inside of the logarithms. So log base 5 of x plus log base 5 of 2 can be condensed down as a single logarithm, log base 5 of 2 times x, log base 5 of 2x. I could do a very similar thing for number 2. First of all, coefficients outside of the log can turn into powers inside the log. So I have log base a of k to the 1/2 plus log base a of x cubed. Now remember that addition outside of the logarithms turns into multiplication inside of the logarithms. So this is going to become log base a of k to the 1/2 power times x to the 3rd power.